So let's talk about the temperature concentration model, except I'm going to change its name to the conduction diffusion model. I'll put conduction over there and diffusion over here, let's say. Since, as you'll see, the similarities, or they're practically the same model, all that's changed from one to the other is the name of the ideas. In one case you call it temperature, and the other case you call it concentration, but the actual mathematics isn't identical. But so let's begin with conduction. All right, here's so I need a simple physical situation that I'm modeling. So imagine a tank of some liquid. Water will do as well as anything. And in the inside is suspended somehow is a chamber. A metal cube will do. And let's suppose that its walls are partly insulated. Not so much that no heat can get through. There is no such thing as perfect insulation anyway, except maybe a perfect vacuum. Now, inside, so here on the outside is liquid. Okay. On the inside is what I'm interested in is the temperature of this thing. I'll call that T. Now, that's different from the temperature of the external water bath, so I'll call that T sub E. T for temperature, measured in Celsius, let's say, for the sake of definiteness. But this is the external temperature, so I'll indicate it with an E. Now, what is the model? Well, in other words, how do I set up a differential equation to model this situation? Well, it's based on a physical law, which I think you know. You've had simple examples like this. The so-called Newton's law of cooling. Which says that the rate of change, the temperature, the heat goes from the outside to the inside by conduction only. Heat, of course, can travel in various ways: by convection, by conduction as here, or by radiation are the three most common. Of these, I only want one, namely transmission of heat by conduction. And that's the way it's probably a little better to call it the conduction model rather than the temperature model, which might be involve other ways for the heat to be traveling. So dt, the independent variable, is not going to be x as it was over there. It's going to be t for time. So maybe I should write that down. T equals time, capital T equals temperature in degrees Celsius, so you put in the degrees Celsius if you want. So it's proportional to the temperature difference between these two. Now, how shall I write the difference? Write it this way, because if you don't, you'll be in trouble. Now, why do I write it that way? Well, I write it that way because I want this constant to be positive, a positive constant. In general, any constants or parameters which are physical, have some physical significance, one always wants to arrange the equation so that they're positive numbers, the way people normally think of these things. This is called the conductivity. The conductivity of what? Well, I don't know, of the system, of the situation. The conductivity of the wall, or if the metal were just by itself, it would, at any rate, it's a constant. It's thought of as a constant. And why positive? Well, because if the external temperature is bigger than the internal temperature, I expect T to rise, the internal temperature to rise. That means dt dt, its slope should be positive. So in other words, if TE is bigger than T, I expect this number to be positive. And that tells you that K must be a positive constant. If I had turned it the other way, expressed the difference in the reverse order, K would then be negative, have to be negative in order that this turn out to be positive in that situation I described. And since nobody wants negative values of K, you have to write the equation in this form rather than the other way around. So there's our differential equation. It will probably have an initial condition, so it could be the temperature at the starting time should be some given number T0. But the condition could be given in other ways. One could ask, what's the temperature as time goes to infinity, for example? There are different ways of giving that initial condition. Okay, that's the conduction model. What would the diffusion model be? The diffusion model mathematically would be word for word the same. The only difference is that now what I imagine is, I'll draw the picture the same way, except now I'm going to label the inside not with a T but with a C. C for concentration. It's in an external water bath, let's say. So there's an external concentration. And what I'm talking about is some chemical, let's say salt, this will do as well as anything. So C is equal to salt concentration inside, and CE would be the salt concentration outside. Outside in the water bath. Now, I imagine some mechanism. So this is a salt solution, that's a salt solution, and I imagine some mechanism by which the salt can diffuse. It's a diffusion model now. Diffuse from here into there, or possibly out the other way, and that's usually done by vaguely referring to that the outside is a semi-permeable membrane. Semi-permeable so that the salt will have a little hard time getting through, but permeable so that it won't be blocked completely. So there's a membrane, you write the semi-permeable membrane outside. Outside the inside. Well, I give up. You know, not membrane somewhere. Sorry. Membrane wall. How's that? Now, what's the equation? Well, the equation's the same, except it's called the diffusion equation. I don't think Newton got his name on this. The diffusion equation says that the rate at which the salt diffuses across the membrane, which is the same up to a constant as the rate at which the concentration inside changes, is some constant, usually called K still. Okay. Do I contradict? Yeah, okay. Let's keep calling it K1. Now it's different. Times CE minus C. And for the same reason as before, if the external concentration is bigger than the internal concentration, we expect salt to flow in. That will make C rise. It will make this positive, and therefore we want K to be positive, just K1 to be positive for the same reason it had to be positive before. So in each case, the model that I'm talking about is the differential equation. So maybe I should, let's make that clear. Or I would say that this first order differential equation models this physical situation, and the same thing is true on the other side, over here. This is the diffusion equation, and this is the conduction equation. Now, if you were in any doubt about the power of differential equations, the point is, when I talk about this thing, I don't have to say which of these I'm following. I'll use neutral variables like y and x to solve these equations, but clearly with a single stroke, I will be handling both situations together. and that's the power of the method.